All right, I have a few minutes. My son is sleeping and I'm going to be talking kind of quietly. Hopefully he'll be able to hear me. I wanted to get this done before you guys had your test on Tuesday, so here's what you need to know about related rates. First, it talks about how related rates and implicit differentiation go hand in hand, but real quick, just to kind of explain. If you go back to chain rule, if you took the derivative of that, would become dy dx, or y prime, it doesn't matter. It'd be the derivative of the outside times the derivative of the inside, right? Now, how does that relate to implicit differentiation? In implicit differentiation, you wouldn't have this function inside. Instead, you might have y equaling, this is a bad example, I guess, but if I had y squared, so I'm substituting sine out for y. You see how it still has the same structure? The function is equal to some function squared. Now again, I wouldn't use y and y squared, but just so you can see, the derivative of y we know is y prime. The derivative of y squared would be 2y to the first power, but think about what you did over here. 2 function to the first power, but you had to multiply by what's inside. So how do I represent this as it relates to that? How do I represent cosine as it relates to sine? That is the derivative of that function. So I need to multiply by the derivative of that function. Anytime you take the derivative of y in implicit differentiation, you will tag on a y prime. These are in essence the same, except this doesn't have all the extra functions on it. Now again, there's more to do in an example like this, but I'll leave that to section 2.5. Related rates is very similar, except now we're not using just x's and y's, we're introducing several more variables. For example, you might hear or you might read about these actual real life, quote unquote, real life situations. In this case, we have water passing through a funnel. If it's a funnel, then we know that we have to use a cone's formula. Now, why volume? Because if water is passing through it, it's filling it up. So there's the volume piece of it. Pi over 3, or 1/3 pi r squared h, is your basic formula for the volume of a cone. You need to know your basic formulas. There will be some that will be given to you, but there will be some that won't. It's just expected that you would know them. For example, Pythagorean theorem, it's expected that you would know. So how would you differentiate related, or a function like this, with respect to related rates? In this case, what you need to realize is that the variable that's changing is t. It's changing with respect to time. It's a rate. Anytime you're talking about a rate, you're changing time. So you'll notice that each of these has t in the denominator, as opposed to when you were taking the derivatives before, they all had x's, because that was a derivative with respect to the variable x. Everything we did was connected to the x variable. Now it's all going to be t. Anything that's not the letter t has to be written in this way. Okay? The derivative of t squared would be 2t, period. But the derivative of r squared would be 2r times the derivative of what's inside. This is a separate function that contains a t. So dr dt gets tagged on to the end. Dr dt would be the same as writing r prime. We don't want to write r prime though, because we actually want the dt to be part of the function so you can see the rate that is being changed. A lot of the stuff that we're going to do is all about dissecting and doing a close read on the word problem. So hopefully it'll make that quite a bit more clear. Here's your original function. This is a variable. This is a variable, not the r squared, but just the r. And this is a variable. I'm going to actually connect pi over 3 with the r squared, so you're going to have to ignore this separation right here. And I'm going to treat that as a coefficient to the r squared. If this is a function for the variable r, and this is a function for the variable h, then you have a function times a function, which is the product rule. Therefore, the derivative of v with respect to time, so volume changing over time, is equal to the first times the derivative of the second plus the second times the derivative of the first. Well, what's the derivative of the first? You keep the coefficient pi over 3. You bring the r squared, so bring the 2 down, leave it to the first power, and because that's not a t, you multiply by the derivative of what's inside, quote unquote, according to the chain rule. Now, to make this hopefully a little bit even clearer, let's talk about the conditions and then we'll go right into a word problem. So what we're going to do first is identify all our given quantities and make a sketch. I think the sketch is probably one of the most important pieces because once you have that labeled, then you can see what information you're given and what information you might be trying to solve for. You're going to write an equation that involves the variables whose rates of change are either given or to be determined. You want a relevant equation. If it says something about volume changing, you don't want to use an area formula, so make sure that you're paying attention to that piece. We're going to use the chain rule. We're going to implicitly differentiate both sides with respect to time. That's our denominator's value. And after completing step 3, we're going to substitute in everything that we know and hopefully be able to solve for what we don't know, what we're trying to actually figure out. So before I get into an actual word problem, we're going to keep it fairly simple and just talk about an equation. When you're talking about related rates as it relates to an equation, you're thinking of the graph of that equation and you're talking about how quickly your x are changing in relationship to your y's, or how quick your y's are changing in relationship to your x's. So it's not a word problem, but imagine that this is happening in real time, that you're seeing this graph drawn and there's maybe a ball riding the graph back and forth, and we're seeing how quickly our x values change as opposed to or in relationship to our y's being changed. So how do we take the derivative? Well, what's the derivative of y? Is y the variable? No, the variable is t. So anything that is not t is considered a function of t, and it would be written as d of that variable over d of t. There's no special condition here, it's just the straight up derivative. Now, how would you take the derivative of x squared? Well, we know it as 2x, but x is no longer the variable, t is the variable. So just like the chain rule, once you're done differentiating this function, you multiply by the derivative of itself with respect to the variable that actually exists. And the derivative of 3 is 0. I won't even put it. Now, reading further, let's see what we're given. It says find dy dt. So this part's going to be missing. When x is 1 and dx dt is 2. I don't know why it says when x is 1 twice. We don't really need that. I can edit that later. So what this is saying to me is that dy dt is equal to 4. Meaning that for every 2 that x changes, y changes 4 at the point 1, so, or at the x value 1. So that's not going to change depending on where you are on the function, but that is what's happening in that moment. As x is changing at a rate of 2 units per second, or whatever you want to throw in, the y is changing 4 units per second at that point. All right, if I was there with you guys, I would change this to be relevant to you. So if you want to take Connor and Garrett out of the problem and put in 2 people in your class, and go right ahead. It says Connor is known for his unruly shenanigans, but this time he's taken it too far. Garrett has decided to paint his house. He's standing at the top of a 25-foot ladder that's leaning against the 2nd floor. Connor decides to pull the ladder, which is currently placed 7 feet from the base of the house. And he's pulling it at a rate of 10 feet per second. Assuming no other parameters, how fast is Garrett falling down? Now, step 1 is a sketch. Sketches do not have to be exact. I mentioned that in your first test. On your first test, graphs need to be exact, but a sketch can just be, you know, for lack of a better word, a sketch. So I'm going to draw a house here What do I know about this picture? Obviously, that's not a full house, but all I care about is the wall. I know that this ladder is 25 feet. I know that Connor decides to pull the ladder and it's currently placed 7 feet from the base of the house. Now, if we're talking about the base of the house, then this right here is 7 feet away. I hope you see that there's a right triangle, and I can figure out this third side by using the Pythagorean theorem. I'm going to do that right now. If you know special right triangles, then this will stick out to you, or Pythagorean triples rather. But in case you don't, I'm going to continue with the problem. Let's see, 49 is almost 50. 50 from this would be 570, so 575, so this is 576. And B is equal to both the positive and negative 24, but because it's the side of a house here, we're going to use just the 24. So we know that in this moment, that ladder is at 24 feet above the ground. So this is asking us how fast Garrett is falling. Well, Garrett is currently here at the top of the ladder. Connor is down here pulling it away. Okay? If he pulls it away, then we're moving in this direction. If Garrett is falling, he's moving in this direction. Being very general, what are those two directions? In what direction are those two arrows going? This one is going along our x-axis, so I'm going to call this dx dt. This one's going downward, so I'm going to call it dy dt. Again, we're talking about the sides of a triangle. Whenever you're talking about the sides of a triangle and not the angle of the triangle, you're talking about the Pythagorean theorem. The Pythagorean theorem is based on this moving side of the triangle and this moving side of the triangle, but this hypotenuse does not change. The ladder is 25 feet in the entire problem. I'm going to treat x as my bottom side, which does change depending on how we are in the problem. Treat y as this vertical side, which does change as the ladder moves down, assuming, like, you can see it. Here's the ladder, and then as it's pulled, it kind of swings out like that. But the ladder itself does not change. Pythagorean theorem, a squared plus b squared equals c squared. Related rate says, now take the derivative of this moving function. 2x, is x my variable or a function? Well, x is not t, so I have to multiply by dx dt. What's the derivative of y squared? 2y. Is y my variable or a function? Because it's not t, it is a function, so I'm going to multiply by dy dt. And the derivative of any constant, even though that's 625, the derivative of any constant is 0. Do not bring the 2 down and all that stuff. Don't do the power rule for a constant. All right, what do I know? Connor decides to pull the ladder at a rate of 10 feet per second. Does he pull the ladder this way or does he pull the ladder this way? This is Connor. That moment is 7 feet. My y value at that moment is 24. And dy dt, how Garrett is falling, is what I'm solving for. Got 70, this is 140. If I get dy dt by itself, that means that I have moved the 140 over, and I divide by 48. Most people won't say that they're moving at negative 140 over 48 feet per second. So what does that look like as a decimal? Something that makes a little bit more sense to the person involved. I'm going to change this to negative 2 point, I guess that's exact. You can see the repeating sixes. So I'm going to change this back to exact 2.916 repeating feet per second. Now, how do I know that it's feet per second? The fact that it is a change in this height, measured in feet, over time, and time is measured in seconds, means that this is feet per second. Does it make sense that it's negative? Well, he's moving down, and if you pay attention to, I think there's something in the write-up here. If not, I would have said it in class. This is just like physics. Direction matters. Okay? Moving on. Air is pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. What picture would you draw? Well, I want to draw a spherical balloon. You can be as detailed with this as you want. It does not matter. I like to put a little light reflection on the balloon. If you want to draw Pennywise attached to that balloon, go right ahead. It says air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Let's use our brains here. The fact that it says a rate means that this has T on the bottom. The fact that it says cubic feet is what? Well, cubic is a cube, so 3, something raised to the third power. What's raised to the third power? What's in the third dimension? And that is volume. So our volume with respect to time is 4.5 feet cubed per minute. Find the rate of change of the radius. Now the radius is a length, so that's just a one-dimensional that's changing over time. When we write its label, it will be feet. So we're trying to figure this out, but it's going to be feet per what time period? Minutes. We're also given the fact that the radius is currently 2 feet. So what equation do I need for this problem? If you want to know the equation, think about what you have. We have volume and radius, and we have a sphere. So I want the volume of a sphere. The volume of a sphere is 4/3 pi r cubed. How many variables are in here? Well, I say variables, but technically they're really functions with respect to t. The volume is changing over time, the radius is changing over time. So I have two functions, two separate variables for those functions. T is not in there, but t is what we're taking it with respect to, the derivative with respect to. 4/3 pi is a constant. It's our coefficient. What's the derivative of a variable that's not t? It's d variable over dt. Again, this is a coefficient, and the constant multiple rule says bring the power and multiply it by the existing coefficient. So that's going to be 3r squared. R is not my variable, it's a function of my variable, so tag on dr dt when you're done. To clean this up a little bit, I'm going to get rid of the 2 3's, and I'm going to start plugging in what I know. I know the volume is 4.5. I know that the radius is currently 2 feet squared. And I'm trying to find dr dt. Now I feel good about this because it's the only variable I have left. Because I have the potential to make this exact, I'm going to give an answer in exact form and also in approximate form. My right side of the equation becomes 16 pi. So that means that dr dt is equal to the exact answer, 4.5 over 16 pi. You should never have a decimal in your fraction, but I can quickly change that by moving the decimal over and creating another place value on the bottom. If I want to get real technical, 45 divided by 160 reduced is 9 over 32. Remember, the pi is still down there. It's radius. We're measuring length in feet, and it's over time, so it's feet per time period, and the time period here is minute. This is feet per minute. But again, nobody's going to say that this balloon is changing at a rate of 9/32 pi. So what I'd rather give is the approximate answer. 9 divided by 32 pi, rounded, is 0.0895. You could round it better than that. There's no specification up here. You'll have to ask Ms. Ali what she wants for the test, or if the test doesn't say, use your judgment. If you round it to here, make sure that you put a 9. If you round it to here, make sure it's 90. If you round it to here, make sure it's 0.1. So whatever you round it to, make sure it's rounded correctly. And again, it's feet per minute. Okay. We've got a plane. This is the flight path of the plane. It's 6 miles overhead. If S is decreasing, so this distance that separates the plane from this tracking station is getting smaller. Does that make sense? As the plane gets closer, let's say it was here, this value for a hypotenuse would certainly be smaller than what it is in the picture. We want to figure out the speed of the plane. Now again, we're looking at a triangle. We're looking at the sides of a triangle. So this is going to be birthed out of the Pythagorean theorem. I don't have a variable up here yet, but what would be a logical variable for a horizontal path? I would use x. So if this is saying what's the speed of the plane, they're asking how far or how fast is the x changing with respect to the time period. This says hour. Doesn't take long to find my time period, hour. So dx dt is what we're looking for. And that's going to be in miles per hour. S is decreasing, so once it says S is decreasing, so S is changing with respect to time, 400 miles per hour. I'm going to be honest, I think it's negative, but I'm going to leave it there for a second, just as it is, and use my brain, come back. I'm just having a little brain freeze right now. S is 10 in this moment, and if I have a triangle with 6 blank 10, then I'm already familiar with the 3, 4, 5 triangle. If I have a 6 and my hypotenuse is a 10, 6, 10, then my middle value must be 8. I didn't have to do the Pythagorean theorem to figure that out. This is a multiple of 2 of the original 3, 4, 5 triangle. You can do the Pythagorean theorem, but knowing Pythagorean triples makes it a little bit faster. All right, so Pythagorean theorem, because I've got sides of a triangle. 6 squared plus x squared equals s squared. The derivative of a constant, whether it's 6 squared or 36, is 0. The derivative of x squared is 2x, but x is not my variable here, it's a function. So you tag on the derivative of the function with respect to time. Same with the s. Now what do we know? Let me bring my work up here. We know that x is 8. We know that we're looking for the speed of the plane, so dx dt is empty. We know s is currently 10. And we know that it is changing at 400 miles per hour. I'm going to leave this positive, and here's why. It's decreasing, but I'm moving in this direction, and that's a positive x direction. If I made this a negative, it would make this a negative, and that wouldn't make sense in the math. So I'm going to leave it alone. There's probably a better way to explain that, but again, my brain's not working quite at 100% these days. So we've got 4,000, this is going to be 8,000. Divide both sides by 16. I should know this. I do not. It is 500. 500 what? Well, x is a linear variable. There's no special, like it's not area and it's not volume. Area and volume behave differently. Area would be something squared, volume would be something cubed, but any other single variable is whatever that distance is. In this case, it's measured in miles. And t in this case is measured in hours. So I am moving at 500 miles per hour on this plane. Okay, in summary, always start a related rates problem by drawing a sketch. I'll even say drawing and labeling a sketch. It's important to have your knowns and your unknowns identified before you even begin, so you know what formulas to use. It might be difficult to remember to use a spherical volume formula if you don't have the balloon drawn. Now there's some clues in the problem itself, but the picture makes it a little bit clearer, at least in my opinion. One absolute truth for related rates is that our variable is t because time changes. And I'll even go further and say these elements change with respect to time. My son's starting to wake up, so I gotta wrap this up. A good way to determine which equation is being differentiated is to look for words like, look for the word rate or speed or anything like that. Look for volume, look for clues, but more than that, look for labels. Okay, by looking for the labels, what we're trying to find, it says, we're trying to find the speed of the plane. Okay, well, what would speed look like? Miles per hour. I know that I'm looking for a direction with respect to time. Doing that kind of dissection, there's a better way to explain this, but sorry for giving you the short end of the stick. Just as in physics, direction matters in related rates. This means negative numbers mean something, like down or to the left. Okay, stuff like that. That the negative actually has a purpose. It's not just a negative number. That's your related rates lesson. If you have any more questions, feel free to let me know. I did put related rates review, obviously in the review for chapter 2, and that's already uploaded on Schoology. All right, good luck on Tuesday.